Alright, Algebra 2, 2-1, reviewing stuff about relations and functions. Chapter 2, by the way, is called Functions, Equations, and Graphs. Very a little vague, I guess. Anyway, so that's specific. So first, the definition of a relation. Perhaps you remember learning that as like a vocabulary word, like a word that definitely meant something in math. A relation is a set of ordered pairs, usually pairs of x and y values. So basically, as long as it involves ordered pairs of numbers, again, usually those variables that are like x and y. As long as it involves ordered pairs, you can call it a relation. So basically, any equation, any graph, any table or list of xy pairs, they're all relations. You know, as long as it involves some relationship, get it? Relationship between like x and y, it's a relation. So, you know, example of a relation, this list of ordered pairs. Another way to show this relation is just by breaking it up into two separate rows or two separate columns with a table. Okay? I call this a list. I don't know if it's an official term. Probably not. Probably something I just say. I call that a list of ordered pairs. And so let's see. So 1, 3, 3, 5, 3, -1 from here, and then -2, 3 from there. Or by graph, you could just plot these points. 1, 3, 2, -2, correct? So 1, 3, 2, -2, -3, 5 is there, right? 1, 2, 3, 4, 5. And 3, -1 goes there. And -2, 3 goes there, I believe. So you can show this same relation by graph, just by showing all these points on a graph. Or by mapping diagram. Here's how you do that. Over here in this, oval, for lack of a better word right now, you're going to have all the x values, and I'm just going to call them x values for now. I wanted to say another word, but too early. Don't want to get ahead of myself. But in here would be all the x values, just grouped together like in one little bubble. And then over here you would put all your y values. But there's a little bit more to the story, but you'll see in a second. 1, okay, and then 2, and then -3, and then 3, and then -2. No repeats, right? Because if there was repeats, you wouldn't need to rewrite a number more than once. So over here we have 3 for all the y's. 3 and then -2. And then 5. And then -1. And then 3 again, which is already here. So we do not have to write it again. And so here's how we finish this mapping diagram. There's always arrows when it comes like the mapping. So 1 maps to 3 with the arrowhead there. And 2 maps to -2 because it's 2, -2. And -3 maps to 5 because these numbers go together as an ordered pair. 3 maps to -1. And -2 maps to this 3 also. Okay, so this would be a mapping diagram you could draw for this relation. Okay, just the x's over here The y's over here with arrows connecting which ones go together. So complicated. All right, here we go. Speaking of what I was thinking of. Speaking of thinking. The domain and range. These are, you know, relation is a pretty, I don't know, big deal as a vocabulary word. Domain and range, even bigger deal, like way big of a deal. Like Ron Burgundy, big deal. You know, like they have leather-bound books at home and stuff. But what does the domain mean of a relation? What's the domain of a relation? It's the set of all of the x values in that relation. Like a list, like a set of all of the x values that are involved in that relation. And the range is the set of all y values. So real quick, couple side notes here, or at least comments. But first the side note. Excuse me. You probably know what I'm talking about when I say that the word range can mean something else in different scenarios, different contexts, right? If you have me right now as a teacher, or if you've ever had me as a teacher, I've probably given you this spiel at least once at some point in the semester, that math vocabulary, in a way it's its own language, but actually, for the most part, I feel like they pick like very, very good words to, to mean things. Gosh. But you know what I mean? Like range and domain and even the word relation, you know? I mean, the fact that they call slope intercept form, again, here I am getting ahead of myself again, but like they don't try to confuse you. Like they don't like make new words out of thin air that are confusing, and I think they pick very good words that actually do the opposite of confuse you. But and moving on here, and it's very rare that a word in math can mean like two different things in two different contexts, two different situations. The word range is definitely one of them, but in this situation, the word range means the set of all the y values in the relation. Tangent is another word in mathematics that you gotta, it can mean different things depending on what you're doing. Then there's the word inverse. That's a can of worms. So be very, very careful with the word inverse, because that means different things. Whew, I'm not even going to go there. But I feel like there's at least one more that I usually can think of. But throw me a comment if the comments are unlocked on this video. Range, tangent, inverse. I feel like there's at least one other big one, but maybe not. If you can think of one, throw a comment down below. But anyway, this is easy to remember, the fact that domain is all the x's and range is all the y's. You could think of it as alphabetical order. Domain and range is in alphabetical order. X and Y are in alphabetical order. But I don't know, man. For me, the way it just fits into my brain is like, when you say domain and range, you literally say domain and range. You don't say range and domain is what I mean. You say domain and range, not range and domain. Just like you say peanut butter and jelly, not jelly and peanut butter, unless you're a weirdo. You say aunts and uncles. You don't say uncles and aunts, right? you say brothers and sisters, not sisters and brothers usually. Mom and dad, you always say it like in that order. I mean, whatever, right? So you say domain and range, domain and range. And you always say x and y. You don't say y and x. You say x and y. So it's very easy to remember that domain is all the x values and the range is all the y values. And I guess not doing any examples with that just yet. Let's talk about, oh, man, the word function. Oh my gosh, that is a big time word. Even a bigger deal than Ron Burgundy. But that's a huge deal. It's like Donald Trump, huge deal, man, in mathematics vocabulary, the word function. But it's a here's the official definition. It's a special relation in which each element of the domain is paired with. I wonder if that's still a typo on your handout. So you might not have to make that change, but I mean, whatever. Where the domain is paired with, well, each element of the domain is paired with one and only one element of the range. Translation, for every x value, there's exactly one y value. Like an x value will only map to one y value, and there's no x values that repeat. And like I just said, they map to only one y value. Is the relation given on the front side a function? So is this, whether you look at this, right, this table, or you look at this list, is this relation also, can we call it a function? Are we able to give it that label of function? And like we see that there's no x values that repeat, but there is a repeat y value, so that's kind of why this is saying here, are we allowed to have repeat y values? And that answer is actually yes. You know, so basically the deciding factor here was, are there any repeat x values? Because if something's going to be a function, it can't have any repeat x values. I know that seems like a double standard or whatever, but so it is a function because there's no repeat x values. But if we added the ordered pair 2, 4, right? You know, now we would have a repeated x value of 2, and that is not allowed. That is a foul on the play. So because of the repeat 2's, repeat x value of 2, which makes it not a function. How about looking at graphs? Do you remember that if you're looking at a graph of a relation, there's a real easy way to tell, there's a real simple test to see if there's any repeat x values, you know, basically whether or not it's a function, and it's the vertical line test. So a function like this, okay, versus a function like this. And allow me to get out my vertical line tool here. And let's use like, I don't know. What color should I use? So here's the vertical line test in case you forgot. If you can draw a vertical line anywhere, and you could think like, you know, you don't have to like literally draw vertical lines. You can just kind of have your pencil or your finger or your imagination and just kind of like, almost like if you had, this was like your pencil or something, and you just wanted to kind of like slide it along your graph from left to right. Basically just seeing if at any point in time, if any vertical line would hit the graph more than once. You see how no matter where you would put a vertical line, it would look once, 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 once. And no matter where you would slide your pencil or your vertical line, it would only hit the graph once. So this is a yes. You know, this passes the vertical line test. But, you know, this graph over here, look, it fails in all kinds of places. You know, because there's basically like almost everywhere. Maybe not there, but basically everywhere else, no matter where you slid your pencil or drew a vertical line, it's hitting the graph in two different places. Look, 1, 2. 1, 2. So anyway, need I say more? I rest my case, Your Honor. This is a no. This fails the vertical line test. And then final little part of this section 2-1, function notation. Function notation. So I don't know, maybe, I guess there's a chance you never saw this before in like Algebra 1. But here's the thing. When you're talking about an equation representing a function, okay, you know, normally you would see the equation written as y equals 5x plus 3. Okay? Where it's y equals all of it. But if an equation not only represents a relation, but you can also go ahead and call it a function, then so you'd be able to use this function notation. So instead of it being y equals, you could say f of x. I'm going to repeat that, okay? Because this doesn't say f times x. This says f of x, where the function is in terms of x. So f of x equals 5x plus 3. So once again, for like the third or fourth time, the way you say this is f of x. And when it's a function, you can use this notation. And so what this says is f of 2. And so here's how we find f of 2. You'll never guess. You just plug in 2. Oh wait, you probably could totally guess that. So f of x is 5x plus 3. F of 2 is 5 times 2 plus 3. And so that's just 10 plus 3, which is 13. And then f of negative 6, you know, where f of x is 5 times x plus 3. F of negative 6 is going to be 5 times negative 6 plus 3, which is negative 30 plus 3, which should be negative 27. Okay? And like here, f of a, this function is in terms of a. Or 5, why do I keep doing that? 5, 6 times a minus 1/3. Oh no, fractions! So f of 2, instead of 5, 6 times a, it'd be 5, 6 times 2 minus 1/3. And so this would be, this cancels. If you have an eye for this kind of stuff, this would be canceling. And so this would be a 3 now, so it would be 5/3 minus 1/3. So 5/3 minus 1/3. Or if you're the type of person to just do like, make this over 1, okay? And then just multiply the fractions as they are together. It would be 5 times 2 and 6 times 1, and you would get 10/6. But guess what that reduces to? 5/3. Either way, you have 5/3, or if you just throw it in your calculator and you cheat. 5/3 minus 1/3 should be 4/3. Correct me if I'm wrong. F of -6 is going to be 5/6 times -6 minus 1/3. So these cancel, and you got basically, well, the negative sort of stays. You have like -5 minus 1/3, which you can do in your calculator, I guess, but -5, like -5 over 1, becomes -15/3 minus 1/3. So now we have common denominators, and so this should be -16/3. Final answer. And that does it for 2-1 as we review this stuff with domain and range and functions. That's it.